All right, guys, welcome to Unit 8 Review Notes. It's our last review notes. Yay! So one of the topics we're going to talk about in this week is the average value of a function. Basically, to find the average value of a function, you integrate it and you multiply it by this. Now, why is that? Well, the way that you find the average, well, actually, let me back up a little bit. What is it the average value of? Well, it's the average value of the y values. So in other words, if you took all these y values and added them up and then divided by how many there were, that would be your average value, right? Because that's how you find an average, is you add everything up and then divide by how many there are. Well, there's an infinite number of y values, okay? And the way that you add up an infinite number of things is by doing an integral. So this is the sum of all your y values right here. And how many y values are there? Well, that's just the distance between a and b. So you divide it by b minus a. So that's our average value formula. Now, an interesting way of looking at this is that it tells you the average y value, in other words, the average height of the function. So suppose this is my function here. The average height would be about here. Now, a way you can tell that is by comparing the areas. As you guys can see here, look at this area that we're missing here and here. Both of those areas should be roughly equivalent to this area up here. In other words, the average height can be found if you just kind of visualize this in your head. Imagine this kind of like being the waves of an ocean. And let's just say that all of a sudden all the waves stopped. Well, all this water up here due to gravity would go down, right? And that would fill in these missing blanks here, and it would fill it in perfectly, so you end up with a flat line or a flat water surface. And so the average value is what you would get if you imagine taking your function and flattening it out. Okay? So an interesting way of thinking about it is that the area above the average value should always be equal to the area under the average value that's not there. Okay? All right. So that's one concept that you'll be seeing this week. All right, next question. We're going to be mainly talking about area and volume today. So these are just some formulas you want to be aware of. The area between two curves can be found by subtracting your two curves from one pair of from one starting point to an ending point. Sometimes those points where you start and stop are where the functions actually intersect. So for instance, you could have this, like let's say this is function f up here, and let's say that this is function g. Well, if they just say find the area between the two functions, well, that's your starting point and your ending point would be where they're intersecting. But they may not always give you intersection points. Like for instance, you might have a situation like this where they give you function f that looks like this, and then function g that looks like this. Well, they never intersect. So in that case, they would just have to tell you where to start and stop. So they'd say, okay, well, let's find the area between a and b. So that would mean only from here to here is what they want the area of. So in that case, though, they would have to tell it to you. All right. Now, another thing to keep in mind this whole time is that you could also be doing integration with respect to y. Okay. So, for instance, if you had x squared minus 4x here, well, over here it would be y squared minus 4y. Also, these are x values here, whereas over here these are y values. And this is a mistake. That should say dy. You guys might want to fix that on your notes there. All right? So you can be integrating with respect to y or x. And something else that's actually pretty important you guys write down is this is going to be the function that's on top minus the function that's on the bottom. So once again, in this case, like f is on top, but g is on bottom. So it would be f minus g in that case, where you have f is the red function, g is the blue. Right? Whereas over here on this side, it's not top minus bottom, it's the function on the right minus the function on the left. So just an illustration of that is like if you had something that looks like this. Well, this would be your f function here because it's on the right side, and this would be your g function. And if you wanted to find the area between them, you would start here maybe and go up to here maybe. I don't know. It just depends on where they want you to start and stop. But to find the area between those two, it's the right function minus the left function. So it depends on whether you're integrating with respect to y or x. Now, sometimes they can cross at more than one point. This is actually not a very good picture. But let's just say I wanted to find the area between here, 0 and 1. Well, here's the problem with that. From 0 to a, g is above f. But after that, g is below f. So when that happens, you actually need to create two separate integrals. Okay? So the area between those two functions from 0 to 1 is going to be g minus f because g is on top on this interval. Oh, this is supposed to be a, my bad. A to 0. But then after that, from a to 1, the f is on top. So you'd have to find those two integrals separately and add them together. Okay? Now that's if you're doing it by hand without a calculator. But if you're using a calculator, there's a shortcut for that. With a calculator, the only difference between this and this is that one's positive, one would be positive, one would be negative if you didn't switch it. Okay? But we can affix that by just putting absolute value bars on it. And then you could just start at 0 and end at 1. You don't have to include a at all. So, and it doesn't matter which way you put these. You could do f minus g or g minus f, so long as there's absolute value bars, you're good to go. But some questions will be hand only, and some will be calculators, so you want to make sure you know both strategies. Okay? Now, if you ever want to find the area between two curves without a calculator, to find where they intersect, you set the two equations equal and solve. And remember, if they intersect at more than one point, then you need to separate that into two separate integrals and find out which function is on top or bottom. Okay? Now, I didn't tell you how to tell which one's on top and bottom, so if you want to add this little note in here, you can. Plug in a point if f is greater than g, then f is on top and g is on bottom. So that's how you would do it. So like if you had two functions intersecting, on your interval, just pick out a point in the interval, plug it in and see which one comes out greater. The one that's greater is on top, the one that's less is on bottom. All right? Because you're not using a graphing calculator, so you're not going to be able to tell. You're not going to be looking at a picture. You can only figure out which one's on top and bottom by plugging in numbers to see which one's greater. All right, next thing you're going to do is you're going to set up your integral, and then you're going to go ahead and do the integration and solve, and that's about it for those. So if you're going to use a calculator, all you have to do is use this little formula, and you're pretty much good to go. You may have to find out where they're intersecting if they want you to find out where they cross, but you guys know how to do that. Just graph them and find out where they intersect. So there's that. Now, the rest of the time we're going to talk about finding volumes of solids with known cross sections. So I'm going to draw some pictures here for you guys as we go through these steps because I think it'll be helpful in bringing these steps alive. So usually what happens is they're going to start by giving you a function of some kind. Like I'll just draw a semicircle here. Okay. This is my f, and this is my g. The distance between these is the base of my shape. And you'll see why I'm calling it the base in a moment. But the distance between the function f of x and the x-axis, which I'm going to call the x-axis just g of x, the distance between those is the base. So notice I did top minus bottom. Now, if you're doing something with respect to y, it'd be right minus left. But I'm going to be doing respect to x here. Now, we have to visualize this thing now going 3D. So I'm going to take my graph and lay it down flat, so it looks like this now. And here is my base that we talked about before. This is my f minus g. Now, we're going to be stacking shapes on top of that plane where the red line is the base of the shape. So for instance, let's say I was stacking a square on there. Well, that would look like this. All right? We want to find the area of the square. Well, how do you find the area of a square? It's base times height, and the height and the base are the same, so it's basically just your base squared. Or you could also stack on top of there a rectangle. Sometimes you can make something like a really tall thing like this. In that case, whatever your base is, we'll call it b, they're going to tell you something like the height is 5 times the amount of b. So in that case, you would have your base is still squared, but you're going to have 5 in the front because the height is 5 times greater. Or maybe you want to stack on top of there an equilateral triangle. The formula for that is this. Maybe you want to stack on there an isosceles right triangle, where these two are the same. You would have base times height, they're the same, so b times b is b squared, cut in half, and there's your area of that shape. Oops, didn't want to do that. Okay, or you could have a semicircle, so maybe stacking a semicircle up there. The formula for that is, oh, I guess I didn't put it on there, silly me. It's pi over 8 times the base squared. Okay? Now, the next thing we want to do is we want to integrate from a to b. This is b, I'm sorry, you said a, and this is b. So what does the integration do? The integration means that we're going to draw a bunch of these shapes and add them all up. In fact, not just a bunch, but an infinite number of them. And as a result, we're going to get this weird looking three-dimensional figure out of it. Okay? And our goal is to find that volume. So when you integrate the area formula that you had, that gives you the volume of your three-dimensional shape. Okay? So we're going to do an example here to bring it to life a little bit. Here we go. The base of a solid is the region enclosed by y equals negative x squared plus 4. That's this one. And y equals 0. That's this line. Cross sections perpendicular to the y-axis. Now, if we're perpendicular to the y-axis, that means our integral is going to be with respect to y. So I'm going to highlight that. That's an important thing to notice. And we're dealing with rectangles. That's another important thing to notice. And their heights are half the side in the xy plane. So let's begin here. Now, the first thing to notice is that we are integrating with respect to y here. So we want to start by getting the x by itself. Let me do this in a different color, though. Start by minusing 4. Now, you don't always have to do this step. If we were finding shapes that are perpendicular to the x-axis, we wouldn't have to do this. But since we're doing shapes perpendicular to the y-axis, we need to make sure that our equation is facing the right direction. So we have a positive and a negative. And that means something. The reason for that is because the positive value means the right side of my graph when you're doing things with respect to y. And the negative portion refers to the left side of my graph. Now, I'm going to draw a picture. Now, you guys don't have to draw these pictures when you solve the problems, but I do think it's helpful in being a little bit more flexible in how to answer them. So I'm going to draw my graph here. There's that. We have the function on the left, and then we have the function on the right. Okay, so how do we do this when we're integrating with respect to y? The base, for step 1, the base with respect to y is going to be right minus left. The green one is the one that's on the right? And that's the positive one. The function on the left is the negative one. Now this is actually easy to simplify. We could just turn that into a positive and add these together and get 2. Like that. So there's my base. All right, step 2. What formula are we going to use? Well, we're doing a rectangle. And a rectangle is your base squared. So it's going to be 2 square root of negative y plus 4 squared. And then some k value goes here. Well, they tell me that the height is half the base. So what's going to go here is a half. So that's my area formula. The final thing we're going to do to get our answer is you're going to integrate this. Now, what do we integrate to and from? That's a good question as well. Well, it has to do with the fact that we are integrating with respect to y here. When you're integrating with respect to y, you're going from the low point to the high point. So we're integrating from here all the way up to there. So in other words, my lowest y value is 0, and my highest y value is 4. After that, you just plug this into your calculator and solve it, and you're all done. Forgot my square there. All right, but there you guys go. So that is finding the volume of a cross-section, or cross-section volume problem. So let's move on to another question here. Got 2 more to go through. Volume of revolution. There's 2 types of volume of revolution questions. There's the disk method, and then there's the washer method. So let's talk about the disk method. They call it a disk because basically it's just another cross-section problem. It just so happens that your cross-section looks like a disk or a circle. So that's basically it. So the first thing you want to do is find your radius. So the next thing you're going to do is you're going to find the area of your circle, or cross section, which is a circle, I should say, which is pi r squared, and then you integrate to find the volume. So let's look at an example and kind of bring that to life a little bit. So here's my shape. They tell me that x equals y squared plus 5. That's a parabola. So that must be this portion right here, right? This whole thing is a parabola, but I really only care about this much of it because that's the part that has the shaded area we're finding. All right, and the next one we're going to be looking for here is x equals 1, and that's right here. Next we have y equals 0, that's right here. So as you guys can see, basically we're just tracing all the portions of this graph that bound the area. Then we have y equals 2. Y equals 2 is basically this line up here. That one they really didn't need to tell us because it's kind of obvious that it stops at 2 because that's where everything meets up at. So it's just the point where they stop there, basically. All right, so there's that. So there's all my pieces. One of the things I noticed when you guys were going through this was having trouble identifying what all these lines were. So it might help to kind of, take a moment to try to match each line to the graph before you begin. Now the next thing you might want to notice is that I'm revolving this around a vertical axis. And whenever you're revolving around a vertical axis, that means we're doing a dy problem. Okay, so the first thing I want to do is I want to find my radius. To find your radius, you do the left function. I'm sorry, you do the, my bad. You do the function minus the axis. Function minus the axis. So my axis is this line, and I'm rotating this function around that axis, the green line there. Okay, so it's going to be the negative y squared plus 5 minus 1. There's my radius. Now we could simplify that. That's pretty easy to simplify, so I'll just call it 4 there. But there's my radius, okay? You guys may notice, by the way, unlike the last problem, I didn't have to get the x by itself because they gave me the problem like that. That's kind of nice. I didn't have to switch the variables around for that one. All right, number 2. The area of a circle is pi r squared, right? Well, I just found out that my radius was this, so let's plug that in. So that's like, imagine taking this line and swinging it around there. And every time I swing it around, it traces out a circle. And so it's going to create like this little bowl shape as I trace it around, as I rotate that area around the axis. So for step 3, if I wanted to add all those areas up and thus create a integral and volume, you just integrate. Now the question is, what do we integrate to and from? We're doing a dy, right? So when you're doing dy, you put the y values on there where they intersect. So what's the y value here? That's 2. And then the lowest y value is 0. So from the lowest y value to the highest y value, that encompasses all those areas. And from here, I would say just type it in your calculator and you get the answer. So that's the disk method. One more, and then we'll be done for the weekend with this stuff. So another volume of revolution is the washer method, and that's because the cross sections look like a washer, which is like a circle with a hole in it. Okay, so they call this the washer method. And when you have a circle with a hole in it, really it's really just finding in order to find this area here of this washer, you need to find the area of the whole circle and then subtract the middle circle away from it. So basically you have one circle minus another circle, right? So that's the idea there. So since you have 2 circles, you're going to have 2 radiuses. One of them is going to be a bigger circle and one's going to be a smaller circle. So you're going to have a big radius and a little radius. The big radius is the one that's farthest away from the axis of rotation. So find your big radius by identifying which function is farther away from the axis. I'm going to call that one f. And the big radius will be that f minus axis. To find your little radius, you're going to identify which function is closest to the axis. I'll call that one c. So your little radius is c minus the axis. And then you just use this formula. This is your big radius squared. This is your little radius squared, and both of them are being multiplied by pi, so we just put it over there in the front. And so you're basically taking the area of a big circle and subtracting from it the area of a little circle, which is a washer. And when you add all those up with an integral, you get a volume of some shape with a hollow center in it. And that's the washer method. So let's go ahead and take a look at an example here. So what I want to do is I want to rotate this area around this axis. Now as I do that, I'm going to be tracing out 2 different circles. It's going to create a hole in the middle, that big, and then a filled in area that big as I rotate it around the axis. So we're going to have a hole here, and then the rest of it is the area we're looking for. So as I rotate this solid, my solid won't actually be a solid, it'll be a solid with a hole in the middle of it. Okay, so that's the idea. Let's go ahead and begin doing what we did last time by identifying all of our pieces here. So my first piece, y equals negative x squared plus 1. Since the x squared is negative, that's an upside down parabola, so that's this piece. Y equals positive x squared minus 1. That's a positive parabola, so that's this piece here. There's my positive happy face parabola. So just this much of it, though, is all we need to look at for now. And we are also having x equals 0, so that's here. So that's pretty much all your area there. And the last one they don't really need to tell us, but x equals 1 is here. They don't need to tell us because the area automatically stops right there anyway because they intersect. But there it is. So I'm going to be rotating that area around this axis right here. Okay. So what two functions are we really working with here? The only purpose of putting the x equals 0 and the x equals 1 is so that we know where to start and stop our integral. Those are our limits, in other words. The other two, the pink and the orange one, are the actual functions that we're integrating. So here we go. Step 1, you want to find your big radius. Which function, the red one or the orange one, is farthest away from the axis? The red one's farther away. So that's this guy. So it's negative x squared plus 1 minus the axis, which is negative 2. Which means we could simplify that to be 3. Okay. Next, let's find our little radius. That's the orange one. The orange line is closer to the axis. So that's going to be x squared minus 1, right? Minus a negative 2. And if we simplify that one, we get x squared plus 1. All right, now by rotating the areas of the circles around, we get pi, and then we have our big radius minus our little radius. And we're going from x equals 0 to x equals 1. And you would punch that in your calculator and get your answer. Now, something that I forgot to mention is, how did I know I was doing dx and these equations were okay? Because I had a horizontal axis of rotation. If you have a vertical one, you would have to get the y's or the x's by itself, right, and do it with respect to y instead. So there's that. Now, some people might have a little bit of trouble understanding the difference between the washer method and the disk method. The difference is this. The disk method is a solid circle, whereas the washer method has a hole in the middle. And that hole happens because the area you're rotating has some distance between itself and its axis. So if you have a function, like let's say I wanted to rotate this area. Let's just say I wanted to rotate this area around this axis. Well, there's a gap here. And therefore, when you rotate this around the axis, you're going to have a hole. Whereas whenever you do the disk method, let's say this is my area, and this is my axis. When you rotate this, there's no gap between the area and the object you're rotating. So you're going to end up with a solid object. Okay, so the disk method has only one radius because it's the distance, it's the axis of rotation is one of its sides. But the washer method has two radiuses because you have this function, which is a distance from the x-axis, and then the bottom of your shape, which is also a distance from the x-axis. So you end up with a gap. So there you guys have it. That's how you can kind of tell the difference of when to use each one. But that's it. So hopefully it was helpful. We'll be putting this stuff to practice in class next week. We'll see you guys then. Bye-bye.